All right, hello, and um, welcome to our Wednesday night office hours. I see that I apologize for our technical difficulties at the end of the lecture. I don't actually know 100% what caused them or why. I thought my stylus battery died, but I think it was something else went wrong with Photoshop because after I restarted, my computer was actually working fine. Hopefully we have audio. I'm just gonna do a redundant check here. All right, let's see. Oh, hello. Hopefully we have audio. I'm just gonna do. Yep. Okay. Good. Okay. We are live. So hello and welcome to anyone and everyone with or without questions. Today I received a couple office hour questions through email. So I'm going to boot those up to answer them. But of course, to anybody who's here live, I will totally answer your questions first. But in the absence of any live questions, I'm going to be hitting up some questions submitted over email. Oh, let's see. Oh, thank goodness. Okay, awesome. I thought my okay. So the first question is actually one regarding naming hydrates, and we have not explicitly covered hydrates in lecture. So I'll do just a little kind of give you just a little bit of background here. A hydrate is essentially it's a compound it is a compound. Whoa, hello. Okay, hang on. Something weird happened with the audio. That's weird. I'm going to check to make sure we're not dead. Up on the server. So it's a compound, essentially. That's weird. Okay, good. A compound with water molecules, essentially stuck. It's got water molecules stuck on it. All right. So, for example, calcium chloride. This happens with compounds that are very agroscopic. That is a word that means they absorb water. They have strong attractions to water. And calcium chloride is one such compound. It has to be stored in a desiccator to prevent water from water from the atmosphere getting absorbed by it. So there's special storage conditions, because when it's left exposed to atmosphere, two water molecules will attach to it. And so the way you'd name this, this stuck part, is signified right here by that green dot. And the number of water molecules that are stuck onto your hydrate are emphasized there. So the way you'd name this is you name it like you would any ionic compound. This is calcium chloride. And then if you're dealing with a hydrate, you're going to add hydrate onto the end of the molecule, and depending upon how many water molecules are attached to your hydrate, you use mono, di, tri, tetra, etc. So this would be calcium chloride dihydrate. All right, so this is calcium chloride dihydrate. If there were only one, it would be monohydrate. If there were three, it would be trihydrate. If there were six, there'd be hexahydrate, etc. The prefix that you use, the prefixes are the same as for naming covalent compounds. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, etc. All right, so that is how you name a hydrate. One last thing I want to point out, and this will become important in Lab 2, which I will be posting soon to my lab section. Other lab sections may already have access to this. But when it comes to when you calculate the molecular weight of hydrates, you include all water molecules. So, for example, if you were calculating the molecular weight of calcium chloride dihydrate, you would need the molecular weight of calcium, which is 40 something. Yeah, 40.08. You'd need the molecular weight of chlorine, which is 35.45. You'd need the molecular weight of hydrogen, which is 1.008. And you'd need the molecular weight of oxygen, which is 16.0. Now, chlorine, we've got two of them. So we need to multiply the 35.45 by 2. But now with hydrogen, we have 2 times 2, or 4 of them. And with oxygen, we just have 1 times 2. And this is how you would calculate. You include all the water molecules in your molecular weight. So we have 1.008 times 4 plus 70.9 plus 4 plus 70.9 plus 32 plus 40.08. So this would have a molecular weight of 147.012. For applying the rules for sig figs, we'd have to round to the hundredths place. And then add our units. So that is how you handle hydrates, both for naming and for molecular weight purposes. Let's see. Okay, Eric, you have a question. For the lab worksheet, should the calculated mass in grams of sodium chloride be the same for both aliquots A and B? Eric, that is a great question. And the answer is yes. Every aliquot taken from the same solution will have the same mass. Which for this experiment will be 1/5 the total. Yeah, man. You are welcome. All right. Okay. So that was the first question for Chem 400 office hours submitted over email. We've got a couple more. I also see we have people joining the live stream, so feel free to throw out your questions at any time. Okay, yeah, awesome. Nathan, let's see. I have a question about exercise 2. Okay, Nathan, let me pull the situation up. Let's see. I'm looking for your problem. Let's see. Okay, here, hang on one second. Okay, so let's see. You've got a question from exercise 2. Identify the name for BE2. Okay. Okay, so here's the deal. All right, let's go ahead and open up our periodic table. Okay, so we've got to name the compound BE, open parentheses, NO3, close parentheses. Then we've got that dot. We've got 4 H2O. All right, so the thing is, and this actually fits in perfectly with what we were just talking about, we know that this part of the molecule is going to get named tetrahydrate. All right, so anything that does not have a tetrahydrate, we know that we're going to exclude. The question is, for this part of the molecule, is it ionic or covalent? Right, because with covalent compounds over here, we use prefixes. And then over here with ionic compounds, there are no prefixes. And so when you look at it, is this ionic? Is this covalent? First off, beryllium is right here. It lands squarely in on the metal side of the railroad tracks. Remember, this is kind of the dividing line between metals and non-metals, where all the metals are right in here. So this is definitely Metaltown. So that indicates that we're dealing with an ionic compound. But another thing that's even more telling that we're dealing with an ionic compound is nitrate, NO3. This is one of our polyatomic ions. Right? So this is definitely an ionic compound, which means that you just name it, name of the cation, beryllium, name of the anion, nitrate, and it will not take any prefixes. Prefixes are for covalent compounds only. So hopefully that clears that business up. All right. We have a couple more questions on email. Of course, interrupt me at any time as I move through these. Yeah, dude. I am so glad I could clear that up for you. Yeah, totally. And again, you got a metal, so that's like, okay, that feels ionic for sure. But also another dead giveaway is you're dealing with a polyatomic ion, so definitely an ionic compound. It's a little weird though, because it's an ionic compound that's a hydrate, so it's, it's a little more funky than your straight up ionic compound. Let's see. When we calculate polyatomic ion's mass, we need to add each element's weight. That is 100% correct. And not only each element's weight, but if you have multiples. So for example, if you were to calculate the molecular weight of calcium hydroxide, this thing has not only the polyatomic ion hydroxide, but there's two of them, right? So here we'd be dealing with one calcium, and not just oxygen and hydrogen, but we have two oxygens and two hydrogens because we have two molecules of hydroxide. Yeah, man. Anytime. So this would have, calcium hydroxide would have a molecular weight of 74.088 AMU, but then we would round, or we'd put a mark to remind ourselves that the last significant digit is in the hundredths place. All right. Okay, so there was a, I did get an email question about entering numerical values in Canvas. Entering numbers in Canvas quizzes. All right, so if your number is positive, then you enter your answer as simply that number. There's no need to put a +1 or a plus sign in front of it. You just enter it as 1. If your answer is negative, you enter your answer as negative sign followed by the number. All right. The wrong way to do this, and I had some students make this mistake over the summer, and which is why I state the wrong way to do it, is if you put number followed by the minus sign. That is incorrect. Canvas will not recognize that answer. And again, with positive numbers, every number is assumed positive unless it's negative. So there's no reason to put a positive sign out in front of your positive number. All right. Okay. I had a question about a student ask, how does KH form? And they were curious because we know that potassium is a positive ion, and hydrogen. This student has had some. Well, we've all had some chemistry in our background, and we know that from acid-base chemistry, H is always plus. But actually, in this compound, potassium is your cation, but your hydrogen, in a very interesting turn of events, is actually an anion in this compound. It's actually a -1, and the way this forms is when you react solid potassium metal with hydrogen gas. These two will react to form potassium hydride, which is a solid, and the balanced chemical equation looks like this. Okay, Jason, let's see. Just wondering, I finished the lab quiz. The score seems lower than I thought. Score includes... Oh, okay, Jason, that is an excellent question. So, the lab quiz had a couple free response questions. That I need to grade manually. So Jason, the lab quiz, when you finish it, reflects your score, assuming, but because Canvas can't grade the free response questions, there's a 0 there for both of those problems. Once the quiz closes, I go back and I manually grade. I read all the responses and grade them accordingly for the free responses. So your score when you finish the lab quiz is your score, assuming that you got 0 on the free response questions. Most people get the free response ones though. So when I go back and grade it again, if you did get those correct, you will see a bump up in your score. So that's the way the lab quizzes go. Yeah, totally. So, and it's always a little bit of a sticker shock because the lab, I tend to not do free response questions on exams. So with exams, you'll get, the immediate feedback of that's your score. But with the lab quizzes, Because it's more conceptual, there usually will be a few, maybe a couple, for response questions on there that I have to then go back and grade. So if the lab quiz felt lower than it should, it's because it probably is. It probably is. You probably did great, or at least scored some of the points for the free response questions. But you won't see that reflected till I go in and grade, and I wait till the thing closes, and then I grade everyone's all at once, so I can be consistent. All right, let's see. I have actually 2 more questions over email. Okay, right. One actually, so one is a typo, and everybody will be getting one point for this question. In exercise 2, oops, there's no, well, there is a C in exercise, it's just not there. So exercise what? Exercise 2. There was a problem in exercise 2 that asked you to name this compound. And this is, again, an ionic compound. Our cation's name is lithium. Our anion's name is carbonate. The answer that was checked as correct in the exercise, which this is not correct, was lithium carbon. So if you ran into this question, just know that I'm going to be giving everybody +1 for free for this one. And if you're like, I thought it was lithium carbonate, why is that lithium carbon? You're totally right. The quiz is wrong. There's a typo there, but everybody's going to get full credit. All right. And then there's one last question over email. This one's more of a conceptual question, and I should probably pull up the periodic table. So we've talked about this kind of borderline between the metals and the non-metals, and we said that everybody under here, under the line, all these super, well, not hydrogen. Let's just make that clear. I've said that all the metals, right, are to the left, but I've also said that these metals kind of under the line over here, that these behave like transition metals. All right. There is one that does not behave like a transition metal. Whoops. Oh no. The one that does not behave like a transition metal is aluminum. Aluminum right here only acts as a main group metal. And we can actually talk about why that is the case a little bit later this semester. We'll actually get into the reasons why aluminum is hardcore a hardcore main group element, but the rest of them tend to behave like transition metals. All right. Okay. New question in the live chat. Oh, sorry about that. Manipulating stuff near the microphone is always a risky business. Okay, let's see. Today during Professor Doherty's office hours, she said that FSC students have access to Microsoft Excel for plotting data and lab. Leanna, I believe that is true. There is a download link somewhere. All right. So with that is actually the end of all of the questions that have been submitted through email. So I am open and available to answer any new questions. Yeah. I feel I remember seeing it at some point. This was back when I first joined FLC, because you can download Microsoft Office as long as you're a student or faculty. But I haven't seen it since. So it's somewhere. Hmm. I actually have never used the one provided by FLC, so I don't know. Um, Okay, let's see. New question. Sorry, hang on. I've got it. There we go. Okay. Said it's into an email I was replying to. Okay. You're having a hard time naming ionic compounds. Yes. We totally can. Tylin, correct me if that's not how you pronounce your name. Here, let's let's dive into this situation. All right, so here's the deal. So when it comes to naming ionic compounds, every name for every ionic compound falls into this pattern. It is the cation name plus the anion name and the only thing you have to change is the very end of the anion name you change to an "ide." All right, that is naming every ionic compound. Cation name plus anion name with an "ide." So, for example, if you were asked to name this ionic compound, and we know it's ionic because we're pairing a metal together with a non-metal. All right, our cation name is aluminum. Our anion, our negative ion, is made up of bromine. But then to get our name right, we switch that ending to an "ide." So it's just aluminum bromide. All right. If we were asked to name, for example, let's do, all right. We follow the pattern. Our cation's name is calcium. Our anion is made up of hydrogen atoms. All right, but then again, we've got to chop off the ending here and add an "ide." So this would be calcium hydride. All right, let's do another one. All right, here, our cation name is sodium. And our anion is oxygen. And to get our ionic name down, we chop off the end and add an "ide." So this would be sodium oxide. All right, it's cation name plus anion name with an "ide" added on. All right, now, a couple things that are worth pointing out. One wrinkle has to do with the transition metals, for example. If I were to ask you to name this situation, our cation is vanadium. The problem is vanadium is a transition metal, and transition metals have unpredictable charges. They can have any number of charges. And so with our main group metals, we just say the cation name, but for the transition metals, part of that cation's name is explicitly stating the charge. So this would be vanadium something. We'll go back and figure out what that is in a moment. But then our anion name is based on chlorine. We just chop off that ending and add "ide." So this will be vanadium something chloride. Now, we need to figure out what goes here. What is the charge on vanadium? And to do that, to answer that question, we need to remember that the charge on vanadium plus the charge of our 5 chlorines is going to be equal to the total charge of this compound, which is 0. So vanadium plus 5 times the charge of chloride, which from the periodic table is -1, is equal to 0. So if vanadium minus 5 equals 0, that means vanadium in this compound has a charge of +5. And so we need to put a Roman numeral 5 next to its name. All right, let's do another example with another transition metal. How about well, let's see. How about this? Let's name this guy. All right. Our cation is W. This stands for the transition metal tungsten. And because it's a transition metal, its charge is part of its name. We need to go back and figure that out. So I'm going to put an open parentheses there to remind myself this isn't done when I name my anion. My anion here is a polyatomic ion. And for polyatomic ions, you just write their name. You don't change the ending. And this polyatomic ion is phosphate. All right. Now, to figure out what tungsten's charge is, we know that the charge of tungsten plus 2 times the charge of phosphate will equal our total charge, which is 0. And phosphate has a charge of -3. So that means tungsten -6 equals 0. So in this compound, tungsten will have a charge of +6. And that is what we put in Roman numerals in the parentheses after tungsten. The name of this compound will be tungsten 6 phosphate. All right. So really, to name an ionic compound, kind of recapping, it's cation name followed by anion name. The anion names for elements end in "ide." For polyatomic ions, they just are what they are. And then for transition metal cations, part of the name is explicitly stating the charge in a Roman numeral following that cation. So that is how you name any and every ionic compound. Oh, let's see. Sorry. Yes. I would not mind at all. Give me 1 second to pull up those problems. Let's see. All right, 1 second. Oh, hang on. There. Okay. Let's see. Chapter 3. Okay. 1 sec. My textbook is loading up. Okay, let's see. 67, 77, 92. Ah. Oh, interesting. Okay. All right, so this is going to be, this is chapter 3, problem 67, part C. And they want us to calculate the grams in, and then part, so they give us a bunch of different samples, but 67 part C says 1 glucose molecule. All right, and they give us the molecular formula, which is C6H12O6. All right, now the strategy here is we have molecules. So we need to convert from molecules to moles, and then from moles to grams. The way you go from molecules to moles is with Avogadro's number. And then the way you go from moles to grams is with the molecular weight. So that's kind of a glimpse into the strategy. Now let's go ahead and get into this a little bit. So first we have one molecule of C6H12O6. And to convert from molecules to moles, we use Avogadro's number because 6.022 times 10 to the 23rd molecules are in 1 mole. All right. So molecules cancel molecules, followed by, now we need to convert from moles to grams. To do this part of the calculation, we need to calculate our molecular mass. And we've got to remember that we have multiples of each of these. So we've got 6 carbons, 6 oxygens, 12 hydrogens. So crunching some numbers here. This is 72.06. 1.008 times 12 is 12.096. And then 16 times 6 is 96.00. Adding these all together now, plus 72.06, gives us a molecular weight of a 180.156. Using the numbers that I just used, we'd be limited to the second decimal place. It's not going to matter because we're given 1 molecule. But we can put this up here, 180.156 grams. Again, remembering that this has 5 sig figs. Now we're ready to crunch some numbers. So we have 1 divided by 6.022 times 10 to the 23rd times 180.156. Gives us a value. My calculator is telling me that my answer is 2.9916369 times 10, let's see, to the negative 20 seconds. All right, but sig figs wise, we can only keep 1 because 1 molecule is just 1. So we round to 3 times 10 to the negative 22nd grams is the mass of 1 molecule of glucose. So that is chapter 3. Problem 67. Let's take a look at 77. Okay, hang on. All right, Anthony, I'm going to totally. Anthony, I'm going to answer your question real quick before we jump into problem 77. So, here's the tricky thing about mercury 1, whenever you're dealing with mercury 1. So mercury 1 nitrate. Mercury 1 is actually a polyatomic ion. All right, it's actually a polyatomic ion. Mercury 1 is Hg2 2+. It's actually 2 mercury 1 ions stuck together. So when you're dealing with mercury 1, you're always dealing with this as a unit. So when you pair mercury 1 with the anion nitrate, we need 2 nitrate molecules to pair to match our charge, because mercury 1 is a polyatomic ion with a charge of +2. We need 2 negative ions to pair with that. So it actually is Hg2, open parentheses, NO3, close parentheses 2. This is the correct answer because mercury 1 comes in a unit of 2 with a charge of +2. Anytime. All right, so let's take a look at 77. The iodide ion is a dietary mineral essential to good nutrition. In countries where potassium iodide is added to salt, iodine deficiency, or goiter, has been almost completely eliminated. The recommended daily allowance, RDA, for iodine is 150 micrograms a day. How much potassium iodide, and iodine is 76.45%, should you consume if you want to meet the RDA? All right, so we've got a couple things going on. We're told that Ki, actually, I'm going to start in a different place. So, first, let's ask ourselves, what are we trying to find? We're trying to find the amount of potassium iodide to consume in 1 day. All right, how much potassium iodide do we need to consume in a day? We're given that we need to consume 150 micrograms of iodine in 1 day. All right, they tell us that. And they tell us that Ki is, where's that percentage? 76.45% iodine. All right? So that means if we take these two things together, we need to eat 150 micrograms of iodine. And if we're only getting our iodine from potassium iodide, that means that we need to, whatever total mass of Ki we're consuming, only 0.7645, right? 76.45% of that is iodine. So if we're getting 150 milligrams from a source that's only 76.45% iodine, well, to find out what mass of Ki we should consume, we need to divide both sides of this equation by 0.7645. We'll cancel off this side and we get a mass of Ki that is equal to, let's crunch our numbers here. 150 divided by 0.7645. We would need to consume, 196.206671. Sig figs wise, we can only keep 2 because of our numerator. So the 6 will round up, and that 9 will round up, so it'll be 200, but this doesn't have the right number of sig figs. So we need to write this in scientific notation. 2.0 times 10 squared micrograms of potassium iodide. So that is the answer for number 77. Next on the list is chapter 3, number 92. Oh, which is, I think, a page over. Let's see. There we go. Okay, let's take a look at this guy. A 45.2 milligram sample of phosphorus reacts with selenium to form 131.6 milligrams of the selenide. Determine the empirical formula of phosphorus selenide. Okay, this is great practice for the exam. We're told that 45.2 milligrams of phosphorus, or here, hang on. First, we're told that we have a reaction between phosphorus and selenium to form some sort of phosphorus selenide. And I'm going to put an X as a subscript for phosphorus and a Y as a subscript for selenium because we don't know what those subscripts are. We're told that we have 45.2 milligrams of phosphorus reacting with selenium to produce, let's see, what is our total? 131.6 milligrams of the selenide. So our mass of selenium then is the total mass of the compound, 131.6 milligrams, minus the mass of phosphorus. All right, so let's crunch this. 131.6 minus 45.2. So that means we have 86.4 milligrams of selenium. All right, so now that we know how much phosphorus we have, how much selenium we have, we can take these in grams, we can take these masses, convert them to moles, and once we have them in moles, we'll plug them in here for X and Y and determine our empirical formula. All right, let's give this a whirl. So I'm doing phosphorus first. We have 45.2 milligrams. Now our atomic masses are conversion factors from to convert from grams to moles. Right here we're in milligrams, so we actually need to do a conversion to get from milligrams to grams, and that unit conversion is 1 milligram is 10 to the negative third grams. So milligrams cancel milligrams. And now we can convert from grams of phosphorus to moles of phosphorus using the atomic mass, which is 30.97. All right, grams cancel, and we're left with moles of phosphorus. So let's crunch these numbers. We've got 45.2 times 10 to the negative third divided by 30.97. So this is 0.001459 moles of phosphorus. And again, remember, this is the value we're going to plug in for X. Now let's take a look at selenium and figure out our value for Y. First step is exactly the same. We need to convert from milligrams to grams in order to use the atomic mass for selenium. All right, now selenium's atomic mass is significantly larger than phosphorus's. It's 78.96 grams of selenium are in 1 mole. So grams of selenium cancel. Now we can crunch our numbers for moles. We have 86.4 times 10 to the negative third divided by 78.96. Moles of selenium come out to be 0.001094. Sorry, not grams, moles of selenium. And this is our value here for Y. All right. Now, these two values, as we said, are the values that we're plugging in for our molar ratio for the empirical formula. So there's phosphorus, and here is selenium. All right, but now we know that empirical formulas are the simplest whole number ratio, so we have to find out what that whole number ratio is. And the first step towards doing that is dividing both sides by your smaller quantity, in this case, the moles of selenium. All right. This will simplify selenium down to 1. Phosphorus will be a little different. So let's see. We've got to go 0.001459 divided by 0.001094. All right, so phosphorus, after we divide the two, is 1.333638, and selenium is a simple 1. All right, now we're one step closer. We have an integer value for selenium, but we're not quite there for phosphorus. This is an instance where we are dealing with one of these pesky fractions, right? So you got to ask yourself, what fraction is 1.3336? Well, this is the same thing as 1 1/3, which is equal to 4/3. All right, so we are going to rewrite this decimal as an improper fraction. So this would be phosphorus with a subscript of 4/3 and selenium with a subscript of 1. Oops. Let me get my color coordination back in action. Now, the way we get to the simplest whole number ratio is you multiply both of these numbers by your denominator so that they cancel here. And so our empirical formula will be P4 SE3. This is the empirical formula for problem 92 from chapter 3. So that is the business. Okay, let's see. Rin for the lab to get density. Okay. Yeah, Ryan, way different. Oh, I'm so sorry to hear that kinetics was god awful. It's not easy, but it can be really interesting. The more time you think about it. Okay, Rin. So getting to your question about density. So the density, and again, this is for experiment 1. Density is the grams of solution divided by the milliliters of solution. And both of these are total for the aliquot. All right, so for density, you don't take 1/5 of anything. That comes in when you calculate the percent mass of sodium chloride. Oh, dude. All right, so Rin, for the mass percent of sodium chloride, this is grams of NaCl divided by grams of solution times 100. All right, now this the denominator for the mass percent is the same thing as the numerator for your density. Where the 1/5 comes in is the grams of sodium chloride, because this right here are the grams of NaCl in 1 aliquot, which each aliquot in this experiment is 20 mils, right? But the total NaCl, so total mass of sodium chloride, was dissolved in 100 mils of water. So because of this, that means that the grams of NaCl in 1 aliquot is 1/5 the total mass of NaCl. So, Rin, you use 1/5 for the percent mass calculation, not the density. and this, what's on the screen now, is the reason why. Of course, yo. Anytime. Excuse me. To anyone who's listening, that was an explosive sneeze. My apologies. let's see. Hey, Sammy. So when you stream a video live to YouTube, it gets added eventually, but it's not immediate. However, there's this weird little quirk. If you go to the channel playlists, I add the lecture to the lecture channel playlist immediately after streaming, and so before it appears on the channel videos, it'll appear in that playlist. So check out I'm not sure if it's there at the moment, but it will appear there first. Let me grab the link. So yeah, check that playlist out here. Hang on, let me just make sure it's been added. Okay. So I actually just after I gave that I was like, check after I literally just now after I told you to check the channel playlist, I was like, let me go make sure I added it, and I hadn't yet. So I just now added it to the playlist. It's showing it's there on my end. It should be reflecting it on your end, but I literally just made that adjustment. So I just added it to the playlist on my end. I don't know how fast it takes it to YouTube to process my edits, but it should be getting there soon. Alrighty, and nope, don't do that. Thanks everybody for coming and hanging out tonight for office hours. This is my sign off. Good luck taking exam 1 over the weekend. Again, it opens on Friday. There will be a post coming from me tomorrow. I'm almost done. Okay, awesome. Have a good night too, Sammy. I'm almost done at about 70% complete writing the exam. Once I finish, I will post more info on it. And again, it opens Friday, and you have a few days to do it. You can check the syllabus for the specifics. Anyways, good luck. Have a good weekend, and I will catch you all on